Okay, in this video we're going to look at building a digital pulse generator. Now when prototyping with a lot of digital circuits, like you see on this board here, there's usually a need for a digital onboard pulse generator for troubleshooting. So you see here this onboard pulse generator, which is push button activated, is used for clocking counters, flip-flops, or GPIO microcontroller inputs. So the first thing I usually do is build an onboard pulse generator. Then I use it for troubleshooting different parts of the circuit on my proto board. So next we'll look at a schematic. Okay, here's the schematic diagram of the digital pulse generator. Now the first thing you notice here is an RS flip-flop made up by two NAND gates. And I'm using the CMOS CD4093 Schmidt trigger NAND gate chip. So this RS flip-flop is a contact bounce eliminator to clean up the contact bounce on the push button switch. So every time we press down on the switch, we get a clean output on pin 3, and that's fed to pin 8 and comes out on pin 10 of the chip, and you'll get a negative going clean pulse. Now if you want a positive going pulse every time you press on the push button, you could add an inverter on the output of this circuit. Now another feature of this pulse generator is if you hold down the push button switch for more than 1 second, you'll get a continuous pulse train, a continuous negative going pulse train out of pin 10. So this circuit here is what generates the negative pulse train, and we'll look at a demonstration to see how this works. Okay, here's a prototype test box that uses the digital pulse generator as we saw in the last clip. Now this push button here, when it's pressed, will generate a nice clean negative going pulse, and that's fed into a counter which will increment the LEDs on this box, as we see here. So every time I press the push button, it will increment the LEDs on the box. Now if I hold the push button down for more than 1 second, the box will go into a continuous pulse train, as we see here. Now there's two time constants we have to look at. Is how fast those LEDs are switched, and the second time constant is how long I have to press down the push button and hold it before it goes into its continuous pulse train mode. So we'll go back to the schematic and have a look at how we can adjust those two time constants. Okay, here's the part of the circuitry that generates the continuous pulse train. Now if we look at the NAND gate here, that's actually the pulse train oscillator, and the frequency of this oscillator is determined by the 100 k ohm resistor and the 3.3 microfarad capacitor. Now if we increase the value of the capacitor, the oscillator will run slower. And if we decrease the value of the capacitor, the oscillator will run faster. Now pin 13 on the input to this NAND gate is the enable-disable pin for the oscillator. So when pin 13 is high, we'll get a continuous pulse train out of pin 11. And when pin 13 is low, it'll disable the oscillator and there will be no pulse train out of pin 11. So what enables the oscillator is actually the push button. When it's held down long enough, this 0.47 microfarad capacitor will charge up and trigger pin 13 to enable the oscillator. Now when the button is released, pin 3 will go low, and the 0.47 microfarad capacitor will be discharged to the diode quickly, and the oscillator will be disabled. So that's how we could generate single pulses and a continuous pulse train using our digital pulse generator.